And now I'll present the barycentric formula. So the barycentric formula is an equivalent form for the interpolation polynomial to the Lagrange polynomial interpolation, and it's derived from the Lagrange interpolation polynomial, and I will show you hereafter how to derive the barycentric formula from the Lagrange interpolation polynomial. But the barycentric formula is more efficient for computational purposes. So let's examine now the formula for the barycentric, the interpolation polynomial in its barycentric form. So the polynomial p at a point x can be expressed as the sum of I equals 1 till n of yi multiplied by ai over x minus xi divided by the sum from I equals 1 till n of ai divided by x minus xi. So basically it's the same quantity here, except here it's multiplied by yi, with ai being equals to 1 over the products of all the possible expression xi minus xj, with j going from 1 till n and j different than I. Now let's calculate the number of multiplication and division that this form or this expression requires. So each ai requires n minus 1 product or n minus 1 multiplication and 1 division. So because we need to evaluate n quantity ai, each one for each point xi, so we have n by n minus 1 multiplication and n divisions. Now when we want to calculate the sum here, the interpolation polynomial, we have n additional multiplication. So basically yi multiplied by this quantity is 1 multiplication. You do it n times, so it's n additional multiplication. So you add it here, you get n square multiplications. Now for the number of the divisions, you have also n additional divisions. Why? Because this quantity here this is 1 division. You don't need to do the, because it's the same quantity, you don't need to do the divisions 2 times. So you do it n times, so it's n divisions. So you add and you get 2n divisions. So n square multiplications and 2n divisions. Now this is already more efficient than the Lagrange interpolation polynomial form, because it required n square multiplication but n multiplied by n minus 1 divisions. For large n, this is already more efficient. But the main advantage of the barycentric form is that if we add a new point x, so we want to evaluate the polynomial at several points x, the evaluation of an additional point x requires only n multiplication and n division. So basically, if you evaluate the AR before, in the beginning of the program, so the AI depends only on the interpolation points. So you evaluate the AI, and then for each point x you need only then n multiplication and n divisions, compared to the Lagrange interpolation polynomial, where you need for each point x n square multiplication and n by n minus 1 divisions. So this is already much more efficient. And additionally, if you want to change an interpolation point xk, if you add an interpolation point xk, then you will need only also n additional divisions and multiplications. So now we will derive the barycentric formula. So the barycentric formula can be derived from the Lagrange polynomial expression. So let's write the Lagrange, the polynomial, the interpolation polynomial using the Lagrange polynomial. So this is the sum from I equals 1 till n of yi li. Okay. And let's express the yi now. Pi j different than I for j going to 1 till n of x minus xj divided by xi minus xj. Okay, and now we will express the denominator. I will call ai this expression, so pi 1 over xi minus xj for j different than I and j going from 1 till n. Okay, and the denominator, I will call it here L of x because it's a function of x. Here pi j equals 1 till n of x minus xj. Okay, now as you can see that if I define this L of x this way, I need to divide L of x by x minus xi to get this expression. So this is equal to the sum of I equals 1 till n of yi L of x divided by x minus xi multiplied by ai. Okay, because here in this sum this includes the x minus xi, so that's why I divided here, so I can have the original here sum that exclude the x minus xi. So now, and this here L of x can even, because it doesn't include here, so this is sum on I going to 1 till n. So here it's a product containing the j, so it doesn't contain the I, so I can even bring the L of x outside of the sum. So it will give me L of x multiplied by sum I equals from 1 till n of yi multiplied by ai x minus xi. Okay, so now we will get the expression for the Lx. So in order to calculate the expression for the Lx, we will consider a special case where the polynomial is equals to 1. So p of x we consider a special case where p of x is equal to 1. Okay, so when p of x is equal to 1, so p of xi is equal to 1. Okay, yi is equal to 1. So in this case, we get that p is equal to L of x multiplied by the sum of I is equal to 1 till n of yi is equal to 1. So ai over x minus xi, and this is equals to 1. So L of x is equal to 1 over the sum I equals from 1 till n of ai over x minus xi. So now we can reintroduce L of x inside of the general case, and then we have the interpolation polynomial. So p is equal the sum I equals 1 till n of yi ai over x minus xi divided by the sum of ai x minus xi I equals 1 to n. So I get the barycentric formula. And now we will derive the barycentric formula. So the barycentric formula can be derived from the Lagrange interpolation polynomial expression. So let's express the Lagrange interpolation polynomial. So it's the sum of yi li with I going from 1 till n. Now let's develop the expression for the li. So it's the product for j different than I, and j going from 1 till n of x minus xj divided by xi minus xj. Now we'll separate the denominator and the numerator. So for the denominator, we'll call ai as being the product j different than I, j going from 1 till n. So this is b, the ai xi minus xj. And now for the numerator, we will define the quantity that I will call L of x. This is the product for j equals 1 till n of x minus xj. Now if I replace these two quantities in this expression, as you can see, the L of x here includes the product x minus xi. So I have to divide here. If I replace L of x inside of this expression, I have to divide L of x by x minus xi in order to have this expression for j different than I. So if I replace these two quantities in the interpolation polynomial, I will have the sum 1 till n for yi multiplied by Lx divided by x minus xi, because as I said, this product here is included here in the product. Okay, this quantity is included in the product, and multiply by ai. Now I can even put L of x outside of the sum, because the sum is on I and this is the product on j, so it doesn't depend on I. So this is equal to L of x, the sum of y equals to 1 till n of ai yi divided by x minus xi. Okay. Now, in order to evaluate this function L of x, I will consider a special case where the polynomial p of x is equal to 1. So when p of x is equal to 1, so p of xi is equal to 1, okay, then if I replace in this expression, so I get L of x, the sum of 1 till n, okay, so the yi is equal to 1 in this case, okay, ai over x minus xi is equal to 1. Okay, so L of x is equal to 1 over the sum of I equals 1 till n of ai divided by x minus xi. Now if I replace L of x in this general expression, then I get the barycentric formula. So p of x will be equal to the sum of ai yi over x minus xi I equals 1 till n divided, multiply by L of x, but L of x is 1 over, so it's divided by the sum I equals 1 till n of ai over x minus xi. So I got the barycentric expression. Now, as a task, I will ask you to write a MATLAB program that calculates the interpolation polynomial using the barycentric formula. So as I did for the Lagrange interpolation polynomial, you can use the same points here, so you can compare to the analytic expression that we obtained. So first you will construct the AI for given interpolation points, and then you will evaluate the interpolation polynomial using the expression of the barycentric. So you can evaluate the interpolation polynomial at one point, or for a vector x of x value and plot the p of x.